Hi, I'm Adil El-Mumni, Rheology Product Manager at TA Instruments. I'd like to welcome you and thank you for joining us for today's webinar. Our guest speaker today is Professor Gareth McKinley. Professor McKinley is the School of Engineering Professor of Teaching Innovation and Associate Head for Research within the Department of Mechanical Engineering at MIT. His research interests include extensional rheology of complex fluids, non-Newtonian fluid dynamics, microrheology and microfluidics, field response fluids, superhydrophobicity and the development of nanocomposite materials. He won numerous awards, including this year's Society of Rheology Bingham Award, the annual award of the British Society of Rheology, and the Frankel Award from the APS Division of Fluid Dynamics. He is presently a member of the editorial board for Rheological Acta, the Journal of Rheology and Applied Rheology. We're delighted to have Professor McKinley speaking with us today. The title of his talk is Large Amplitude Oscillatory Shear Flow, LAOS, for Rheological Fingerprinting of Complex Fluids and Soft Solids. Gareth?
Thank you very much, Adil. What I would like to tell you about today is a technique that we can use in rheology called Large Amplitude Oscillatory Shear Flow, or for short, LAOS. And the idea I want to get across to you is the idea that you can use this as a way of characterizing not just the linear properties of a material, but also the nonlinear properties of the material. And the idea that you might develop what I call a unique rheological fingerprint that's a unique identifier of a particular material. This is work that's been going on in my group at MIT for about the last 5 years, primarily with Randy Ewalt and Trevor Ng, as well as a couple of other graduate students. So first of all, I should clarify that Laos, or Laos as some people refer to it, is typically thought of as a small Southeast Asian country. That's not what we're interested in today. What I want to do is to think about this as a way of characterizing material properties. And the kinds of materials you might be interested in include things like complex fluids, maybe shampoos, consumer products, as well as food, such as bread dough. And then I'm also going to use a model biomaterial, which is a snail slime, as an example of a weakly cross-linked hydrogel material that has a very complicated rheological response. And then I'm going to move on towards the end to think about materials that also have a yield stress. A good example would be a carbopol gel, or the kind of gel that you would find in a soft soap or a hand cream. So those are the topics for today. I want to start with a few fundamentals, and what we're going to think about is this idea that's shown in the top right of the slide now, which is what I'll call a Lissajous curve, which is a shape that's a unique identifier of the rheological response of a material. Okay, so I'm going to try and be a little bit more sophisticated than this. We'll start off at very basics levels, just explaining the basic fundamentals, and then after we've got the basics of Laos down, then what I'm going to do is try and build up to really the state of the art of where we are in research in the field. And there's a link attached to this presentation where, if you're very interested in the most recent developments, there's a review article that we wrote last year that can give you a lot of the background, as well as examples in a very, very wide range of different kinds of materials. Okay, so what's our motivation? Well, what we really want is we want a rheological test that really exploits the capabilities of a modern rheometer. So we all know how to do small amplitude oscillation. Everybody may be familiar with doing steady shearing deformations, but there's a wide range of other kinds of tests that a modern rheometer can do. And typically, if you have a complicated material, then you really want to push the material into the nonlinear range and try and understand the response not just in the linear viscoelastic range, but also the nonlinear range. And I'm going to introduce to you a framework to do that that's really described by a guy called Pipkin back in the 1970s. And so the plot that I'm showing you is a two-dimensional plot that I call a Pipkin diagram. On the horizontal axis is frequency. So for those of you who know how to do frequency sweeps, that's a very simple test to do, where you load your sample into a rheometer, and then you progressively increase the frequency as you move towards the right of the curve here. Typically, you have to do that at a small strain amplitude. So on the vertical axis here, what I'm showing you is the idea that we might also quantify the strain amplitude of the response, and that's an input parameter typically to an experimental test program. Pipkin kind of sketched out what is known about this space, so here's his original sketch from his lectures. Down in the bottom left-hand corner, what you can see is what I would call Newtonian fluid mechanics, infinitesimally small strain, and infinitesimally small Deborah number, or a measure of how viscoelastic the material is. If that's 0, then you just have a Newtonian fluid. As you moved progressively to the right, then you start to see linear viscoelasticity, and that can be described using the idea of a convolution integral. And eventually, if you go to the far right-hand side, then you end up in the elastic limit, or infinite Deborah number, where the material is purely elastic. However, if you increase the amplitude, so you now move up vertically, then if you do that at small frequencies, you're in what people would call steady shear flow or viscometric flow limits, and that's where we measure typically a shear rate dependent viscosity. If you go right over to the right-hand side and to large strains, then that's the limit of neo-Hookean elasticity or finite strain elasticity. And what Pipkin pointed out is that right in the middle there, which is the space we're typically interested in, so moderate strains and moderate frequencies, it's very little is really known systematically about what goes on in this region. You might hear people talk about a Weissenberg number, and if you think about what a Weissenberg number is really a measure of how strong the flow is in this flow, and I can think about that as being this red arrow that I've shown here, that as you increase the Weissenberg number, what you're really doing is increasing the strain amplitude or the frequency such that the product is what I'll call the shear rate, and you go from the lower left where everything is nice and safe and comfortable out into the wild unknown where dragons and nasty things live, and that's what we really want to try and understand today. The final sketch that I've shown here is this example of a Lissajous curve that I introduced on the first page. And what that is the idea that at every point in this two-dimensional space, you really are measuring a stress. That's recorded by the rheometer and the software, and you can easily display this as what I'll call this Lissajous curve, or more formally correctly, a Bowditch curve, or a Bowditch-Lissajous curve. And it's typically shown there as this nice elliptical response where the stress is a function of time, and it's a function of what frequency you imposed and what strain amplitude you imposed. And we're going to look at a lot of those curves as we go forward. What I really want to do is to teach you what the anatomy of that curve looks like. And as an example, we're going to use snail slime and a few other kinds of materials as just model kinds of complicated materials. Before we do that, however, just a quick refresher on some simple geometry. What I've shown here is the idea that if we put in a strain amplitude, so typically you'll put in an oscillating strain amplitude. Gamma here is the strain amplitude, omega is frequency. What you measure is this idea of a stress, tau, and that has an in-phase component, which I've shown in red. That's the elastic component. And then it has an outer-phase component in blue, which is the viscous component. So you'll notice that time is a variable in this equation. However, when we think as rheologists, time is really something that's just the time taken to do the test. What we want is the measure G primed and G double primed, and how that varies as a function of, say, frequency or maybe strain, but typically not time unless we're dealing with curing materials. So I want to eliminate time from this equation, and you can do that with a little bit of algebra. And what I've shown here, if you do that, you remember sine squared plus cos squared is equal to 1. You play around with the identities a little bit, and you get the equation shown in a yellow box here. And if you look at that, that is an equation of an ellipse. And so the basic idea is that if you get rid of time out of your data, what you have is an elliptical response, and I'm going to plot that with strain on one axis and stress on the other axis. If you have a purely viscous material, then the response basically looks like a circle. Okay, so the stress is out of phase with the strain. When the strain is maximum, the stress is 0. And then as you oscillate, the stress climbs until you get to a maximum strain rate, and then it decreases, and this is a periodic kind of response. If you're dealing with an elastic dominated material, then really what you're seeing is the same information, but you're seeing it from a different viewpoint. So you're really looking at stress being plotted just as a function of strain, and now the stress increases linearly with the strain. When the strain is positive, the stress is positive. When the strain is negative, then the stress is negative. And for a real viscoelastic material, what you're seeing is a projection of this that's somewhere in between. So it's not a perfectly out-of-phase material. It's not a perfectly in-phase material. It has a phase angle, and that's what we usually call delta. And you can think about that as really the angle of the ellipse. Okay? That's not how modern software does the calculations, but at least physically, that's the way of thinking about G primed as being a measure of one component of this ellipse, and G double primed as being the other component of this ellipse. Okay. If you're interested in more reading on this, then there's plenty of online resources, for example, at Mathematica. Okay, so that's a little bit of basics. If you're interested in more details of the geometry, I've given you a lot of references here where you can think about ways people have used to describe the nonlinear properties of these curves. starting with Pipkin, building up through particularly groundbreaking work by Cho and colleagues in South Korea. And then there are many different ways of describing nonlinearity. So I'm going to introduce to you a couple of them today. If you're a fan of good hi-fi systems, then you'll probably remember something called harmonic distortion. Effectively, what we're doing is describing how nonlinear or how anharmonic the response of a particular material is. And this field really started in rheology in the 1960s with Vladimir Filipov, who won the Bingham Medal back in, I think it was 1967. And in those days, he used an oscilloscope. And here's a picture from his original paper, where the idea was that he was looking at a shape. And the shape was now no longer a perfect ellipse. No matter how you looked at it, this shape was no longer perfectly elliptical. And you have to describe distortions of this by thinking about different harmonic information. And that's what we'll be doing as we go forward. Okay, so the way we typically do that in a rheometer these days is not by looking at shapes of ellipses, but by actually using Fourier analysis. So within the computer, a Fourier transform is taken of the signal, and then we look at the harmonic components of that. And so I've shown you here 3 plots. The magenta plot is the input signal. That's a perfect oscillating sine wave. And then the blue curve here is what happens if you have a material with a small strain. And you're effectively thinking about slowly deforming a material. Maybe you can think of a bowl of spaghetti as a set of entangled chains. And you're looking at a small strain in blue, and you can see that it looks like a perfectly harmonic signal. If you increase the strain and you pull that material even more, however, the signal starts to become more complicated, as shown in the red curve here. And if you take a Fourier transform of that, then what we typically plot is frequency along the horizontal axis and amplitude along the vertical axis. And here's an example taken from some work by Manfred Wilhelm on an entangled material. And you can see not just one harmonic, but you can see a second harmonic and a third harmonic. And in fact, you can see all the way down to about a fourth or fifth harmonic very clearly here. So modern instrumentation, because this is all done digitally in the rheometer, you can get signal-to-noise ratios of over 100,000 to 1. That's 5 orders of magnitude on a logarithmic scale, as you can see here. So that goes from a power of 1 down to a power of 10 to the minus 5. So that's a way of doing it. That's typically called FT rheology or Fourier transform rheology. And what you're getting out is a nice series of digital information. What I want to do is to try and tell you what we can do with that digital information. How do we use that to understand a particular material? Okay, so here's an example of an unknown material. This is actually the hydrogel that's secreted by a snail as it crawls across a surface. Typically, a snail uses that for locomotion, so the material needs to have a certain stress associated with it. And it's an example of a hydrogel. It's actually over 99% water with a very, very small amount of a polymer called a mucin inside it. And I've shown you here an AFM image that was taken by some people in Bristol, UK, that shows that it's a very weakly disconnected gel, weakly entangled. If you work out the entanglement length, what I'll call Xi here, it comes out to be about 30 nanometers. And so you've got really this gel that's got polymer chains held together with a bunch of water. The left-hand figure shows what you would put if you would put this material in your rheometer and you just measure G primed and G double primed. And you can see the curves are essentially flat. Okay, I can measure both G primed in black and G double primed, hollow symbols here. And you can see that they're rather featureless, even out to large stresses. Okay? Beyond a critical stress, at a certain point, suddenly you no longer get any data. And what happens there, the modulus decreases and suddenly collapses. That's the yield stress of the material. And you have to exceed that for the snail to be able to crawl forward. In fact, if you ever want to make an estimate of the yield stress of a snail slime, all you've got to do is take the snail off the wall, weigh it, and you find its weight, mg. If you look at the area of the contact patch, stick it back on the wall, it'll give you some idea that the yield stress for a typical snail is somewhere between 100 and 1,000 pascals. So clearly it doesn't look like anything very interesting is going on here. So maybe what the next thing we should do is do a frequency sweep. So we go faster and faster and faster, and that's what's plotted in the right-hand figure here. And you can see that, again, the result is rather featureless. So the gel is elastic. G primed is higher than G double primed. But again, there's really very little in the way of useful information here. So you really have to look at the material in the nonlinear range to understand something about what's going on. And so if I look in the nonlinear range out here at large stresses just before the material yields, if I actually look in the software at what's going on, then what I'll find is that the curve is no longer a perfect sine wave. Indeed, there are higher harmonics. what I've plotted here is in red is the first harmonic, then the third harmonic, then the fifth harmonic. And you can see that the material is definitely no longer a perfect sine wave. Okay? The curve in blue is the raw data that comes out of the rheometer. And then the curve in green is a two-component approximation. So that's capturing the first harmonic and the third harmonic. And I'm going to show you how we can use that information to understand what's going on in the material. Before I go on, one thing I will point out is that in all of these cases, we're typically using roughened plates. So these are roughened plates with a small gap, typically about a 0.2 millimeter gap. That's very important in these kinds of materials to ensure that you don't get slip at the wall. So I'm not going to say anything more about that, but we've always ensured that we are not getting slip when we do these measurements. Okay, so I've shown you that we can get harmonic information out of these kinds of materials. What I want to introduce now is a physical explanation of what's going on and how you might use that in your own kind of experiments. Okay? So what I'm going to introduce here is this idea that the general Fourier representation, which says stress is an infinite series of sines and cosines, is mathematically rigorous and complete, but understanding what G double primed n and G primed n are is rather difficult, and I want a more physical interpretation. Okay, so we're going to base this on work that was done by Cho and Lee in 2005. And their basic idea was to think about the idea that when you've got a material in a rheometer, you've got two orthogonal inputs. You've got, along the x-axis, if you like, you can think about strain as a variable, and that's what I've shown in red here. And on the y-axis, orthogonal to that, you can think about the derivative of a strain, which is a strain rate. Okay? And I've shown that in blue. Okay? So we're going to call those x and y, and then the material response is really a function of x and y, and we're going to think about plotting that on the third axis. Okay? And so your unknown material, which is the sample in yellow here between your parallel plates or your Conan plate, is really an example of what a mechanical engineer would call a transfer function, or its material response connects the strain input and the stress output of the material. And so I'm going to write that in terms of a set of polynomials that people call Chebyshev polynomials. And they're given the symbol T, typically. And so the stress is a component that's elastic. That's the component in red. And then it's also got an additional component, which is the component in blue, which is the viscous response of the material. It's still an infinite series of sums, and so I've got to sum up all of these different components. And the coefficient in front of the red term is called E, and E is for elastic. And the coefficient in front of the blue term is V for a viscous component. But the thing to notice about this equation that I've put at the bottom of the page there is that time no longer shows up in there. So you're really now thinking about stress as a function of strain and strain rate, not as a function of time. And that's the formalism that we're going to use. And then included within typical software packages these days is a way of reconstructing the total stress, if you want, from these individual coefficients. Okay, so I mentioned that these polynomials are called Chebyshev polynomials. The reason they're called T, not C, is because another translation of Chebyshev would have a T at the front of it. Chebyshev was an extremely well-known mathematician in the late 1800s in Russia. For those of you who are polymer scientists, Markov is a name that you might be familiar with. That was one of his graduate students. And if you're a dynamicist, Lyapunov was another person who worked with him who's very, very well known. But these are the right polynomials for describing complicated materials for a couple of reasons that I've put on the slide here. Firstly, they're orthonormal. What that means is that they integrate from 0 to 1, and each mode, which I've shown here in the plot, is orthogonal to the other one. So the first mode is in red here. The second mode is shown in green and then in blue. And if you integrate those across the domain, then they're orthogonal to each other. That means that I can describe complicated functions in a series of basis functions where one mode doesn't interfere with the next mode and the next mode. I'm also going to tell you that those coefficients, V and E, tell you something about shear thinning for the viscous coefficients, and also about whether the material is strain stiffening or if the amplitude gets larger when I put larger strains in it. If you really, really want to reconstruct the time series at the end, if you really want to see the input thing, the other thing that I've shown you at the bottom here is that there's a very common identity that's known that relates the Chebyshev polynomial on the left to the sines and cosines of a function on the right-hand side. And as a little homework example, you might remember as a kid learning that the cosine of 3 times a number was 4 times the cosine cubed minus 3 times the cosine of the number. And you can easily get that from these Chebyshev polynomials if you take T3 of x, and you substitute that x is omega t, or sine omega t, then you'll get the result that I show you there. So that's just a good way of reminding yourself of these kinds of formulae that you may have learned back when you were in school. And you can use this for T5 to find the fifth order polynomial as well. Okay, so those are the material functions that we're going to use. The final thing that's really useful about these is interpolation. So let's say that you've made a measurement at a strain amplitude of 0.1 and a strain amplitude of 0.5, and then your boss says, well, what's the result at a strain amplitude of 0.3? Well, you can easily find that by interpolating. Chebyshev polynomials have optimal interpolation properties. That means they have the least error available if you use the function of the 2 points you've measured to find a point in between. Okay, and so that's going to be very useful when we want to reconstruct arbitrary properties. Okay, so those are the properties. I think the best thing to do now is to maybe think about an example. So let's think about a material that is maybe a hypothetical material that's purely elastic. So the stress is only a function of strain. And I've shown as a sketch here a nonlinear function where the stress is increasing with strain. Okay? So how would you describe that? Well, I've given you the result. Okay? So the result here is a quadratic equation for the modulus. That means that if you multiply modulus by strain, you get stress. So it's really a cubic equation. If you were to put this material into the rheometer and you were to do small amplitude oscillations, if the amplitude was small enough, particularly smaller than gamma star, as I've shown here, then you just stay in the linear regime. So you're just putting very, very small amplitude deformations in. When you do that, then you'd get the red curve that I've shown you here. So that's a linear response. Stress is in phase with strain. Okay? As you start to deform the material into the nonlinear range, then if I go back to my idea of an ellipse, then you're really looking at this as a linear material. And then as I get into the nonlinear range, you're actually looking at beginning to bend this material into its nonlinear shape. Okay. And we can easily think of that as a sine series, as I've written down here. That's what a rheometer would see. But if we represent it in terms of these mathematical functions called T, or Chebyshev polynomials, then it turns out that you can very simply represent it as having only two modes, E1, which is the linear mode, and then nothing in E2, nothing in E4, nothing in anything higher, because they're all orthogonal, and there's just a small contribution from the third harmonic, E3. Okay? So for the blue curve that I've shown here, you'd get the results that's shown in this plot here. So one really important thing to remember here is that if you were to look at the magnitude of this first term, E1, so the large bar that you see here, it's actually been polluted by the nonlinear deformation. And so if you were only to plot out the first component, E1, or G primed as you might call it, it's actually been corrupted by having a small amount of the nonlinear term in there. So you have to remember when you're using an unknown material in a rheometer that if you're in the nonlinear range, even if you're measuring from the rheometer software G1 primed or the first harmonic, it's actually got some information about the third harmonic in there. How do we find that information? Well, you just look at the next harmonic. So if you look at E3, that would be called G3 primed. And E3 here is a positive number. That means it's strain hardening. And you can see the amplitude of it depends on gamma 0 squared. So as you go to larger and larger strains, this component grows larger quadratically. If you're familiar with this notation that people have used in the past of G3 primed and G3 double primed, you'll see that there's a little potential confusion here because those numbers turn out to be negative, and that doesn't have a very good physical feel to it. So what does having a large negative G3 primed mean? I'd say I don't really understand what that means, but saying that it's got a positive nonlinear coefficient that tells me about strain hardening gives me a direct measure of how nonlinear my material is. And so these elastic moduli and viscous moduli are just a good way of seeing that information. Okay, there's other ways of describing the shapes of these loops. Okay, so as we start to look at these Lissajous curves, you're going to see that they're complicated shapes. And so we've proposed a couple of different ways of doing that, particularly what we'll call a small strain or a minimum strain modulus. So M here is for minimum. And then a large strain modulus, G prime sub L, which is the modulus at very large strains. The way they're defined is shown schematically in the first plot here. The minimum strain modulus you can think of as the slope of an ellipse. And then the large strain modulus you can think of as what people would call the secant modulus, or the intersection of the value of the stress divided by the value of the strain. Those are directly connected to the Chebyshev polynomial coefficients. They're not new definitions. Particularly G primed M, you can see, is just a sum, as shown in red here, of the first coefficient minus 3 times the third plus 5 times the fifth, and so on. The large strain modulus, which remember is the secant, so it's the stress divided by the strain, is nothing but the sum of the first plus the third plus the fifth. So it's a very simple way. If you've got these all in the computer, you just add them all up, and that gives you the large strain modulus of the material. Okay. So the final thing you might like to know is to take a material that's not just a perfectly linear material like this. You might want to think about a nonlinear material. And so here's a nonlinear material that rheologists always like to use when they're thinking about things. So this is a piece of silly putty. I'm not going to use it the way we would normally do to bounce it on the desk, but I'm going to use it as the idea that if this was a circle that you were looking at like that, it'd start to deform into a more complicated shape. And clearly I can't describe this kind of shape by just 2 parameters. And so we really need to think about different kinds of measures of the material properties. And so for a softening material, as I've shown in the middle curve here, the material has a large strain modulus, G primed L, that's lower than the small strain modulus. So the material softens. For a strain stiffening material, the large strain modulus actually gets larger than the small strain modulus. And so that corresponds to G primed L being bigger than the minimum strain modulus. And a simple way of taking ratios of those is shown here by what I call a strain stiffening parameter, where I really have the idea that a material that's soft has curves that look like this, and a material that's strain stiffening has a curve that has the opposite kind of deformation. And again, we'll look at that for a typical couple of materials as we go forward. So just a final thing to remember is that in the small strain limit, of course, everything has to collapse back to a linear viscoelasticity. So I've shown here on the left-hand side our snail mucus in a small strain experiment where we're putting in small amplitude strains. And you can see that the modulus that we measure is the same whether we use the large strain or the minimum strain. And that's because it's just described by linear viscoelasticity. It's only when you get to large strain, so the plot on the right is 320% strain amplitude, that you can see that this biopolymer gel strain stiffens. So as I pull the chains, the large strain modulus actually gets quite a lot larger, and it can be up to a factor of 5 larger than the small strain modulus. And you wouldn't see that if you were just looking at linear viscoelasticity. And so that's where measuring the nonlinear properties of the material are very important. And that would show up as basically a measure that E3 over E1 is a substantial percentage of the strain cycle. And I've shown that at the bottom of this curve. So that really concludes the first part of this presentation where we thought about introducing this idea of this framework. What I want to do in the second part is use this idea of what I call a rheological fingerprint, that this is a unique way, now that we can make these measurements, this is a unique way of identifying a new material, just like a fingerprint is a unique identifier of a human being. And what we're going to do is we're going to use these E's and V's, these kind of material measures, as a way of boiling down a complicated Lissajous curve or a complicated fingerprint into essentially a digital fingerprint that says that if I can measure these parameters about a material, then I know everything that there is to know about the shear response of that material. So we want to think about what that set of metrics is. And as an example, I'm first going to use a common material that you might find in, say, a shampoo. So this is a worm-like micellar fluid. And the reason that's useful to a rheologist is because in the small strain limit, the linear viscoelastic response of this is well described by a Maxwell model, which is the simplest model that we all learn. So I'm going to plot the stress on the vertical axis as a function of strain on the horizontal axis, and I'm going to construct that Pipkin diagram that we introduced at the beginning. And so here are a set of measurements for the response of a worm-like micellar fluid. At the bottom left, you can see a circular response. That's a purely viscous response. And as I move to the right, you can see that the material becomes increasingly like an elastic solid, so the stress becomes more and more in phase with the strain. So that's linear viscoelasticity. As I go up to larger and larger strain amplitudes, however, so 100%, 300%, or even 1,000%, you can see that the material becomes a non-linear viscoelastic material, and you can see that these curves are definitely no longer ellipses. They're much more complicated shapes. Okay? The elastic stress is shown as the red dotted curve in the middle here, and that's the linear elastic response of the material. And you can see, again, that at low strain amplitudes, that's a linear response. As I go to larger and larger strain amplitudes, you can see that the elastic response becomes more and more nonlinear. So we can take these kinds of measurements and we can compute E's, the E1 and E3 of them, and I can plot contours of these things. And so here's contours of the first harmonic coefficient for elasticity, or G1 primed, or E1, the elastic modulus. And you can see that it starts from blue, where the modulus is very small at low frequencies, and then the material becomes increasingly elastic, and it approaches a plateau, which is what we would call the plateau modulus in orange. If I go to high frequencies, though, and I now increase the strain, you can see that I fall off that plateau modulus, and you can see the material definitely strain softens. So you can see the idea of strain softening in this material. And this is just the first coefficient of really what is a large number of material coefficients that characterize it. So the next thing I want to do is I want to rotate that to now think not about stress versus strain, but to think about stress versus strain rate, and that allows me to see the viscous response. So now we're plotting stress on the vertical axis and shear rate on the horizontal axis. So we're basically rotating things, and so here's the nonlinear viscous response of the material. At low strains and low frequencies, it looks like a Newtonian viscous response. That looks like a Newtonian fluid. As I go to larger and larger strain amplitudes, you can see that the material softens, or it becomes shear thinning. And then as I go to larger and larger strain amplitudes, you can see this appearance of loops. And I'm going to talk a little bit more about these loops in these Lissajous curves as we move forward in this presentation. So again, I can plot contours of some of these. So let's take one of these looped configurations, and let's probe that a little bit more detailed. What is it about that material response that shows up as these loops? And what it is that there's a substantial nonlinear coefficient. The V3, or the third order viscous coefficient, is indeed largest in that region where the loop appears. And that tells you that in this region, the material exhibits a very nonlinear viscous response. And this happens at a moderate frequency and a large strain amplitude. Okay. Finally, the thing that I want to point out is that these are really, what you're seeing is two-dimensional projections of a three-dimensional surface. And so here is the plot as a three-dimensional surface. On the horizontal axis is strain and strain rate. And on the vertical axis, I've plotted the stress that's been measured for a series of different strain amplitudes. And when you look at this, what you're really seeing is you're seeing different projections where you can either look at the material as stress versus strain. That's what's shown here. You see the linear region going to the nonlinear region, or I can rotate the whole thing by 90 degrees, and I can look at the stress versus the strain rate. That's where these loops appear. But you can see when you look at this in 3 dimensions that the only reason those loops appear is because of the nonlinear complicated shape of this surface. There's not really a loop in there. It's just because you're looking at a particular projection. Okay, so this is all of the information that you can see from nonlinear viscoelasticity. Okay, let's go back to our snail slime. Here's our material response now that you remember was featureless when we looked at it in small amplitude oscillation. And that's because everything looked like an ellipse at small amplitudes. That's the middle region of this curve. But if I blow it up and I look at larger strains, particularly at like 1,000% strain, then you can see that this is a very strain stiffening material. You see this large elastic modulus. And this actually turns out to be a hallmark of many biophysical gels. So if you're interested in actin gels or cytoplasmic gels, you typically find this strain stiffening material response, even though you can't see that if you just do small amplitude oscillations. So another reason why you might want to characterize a material in its nonlinear response. Okay, another way that we might use these kinds of ideas of material measures is not to characterize a material, but maybe once I've made the measurement, to actually fit it to a model. That might be used by colleagues in your company, maybe for numerical simulations, or it might be used as a way of fitting to an existing theory. And so now what you want to do is you want to take all of this complicated information and you want to collapse it into something a little bit simpler. So one way of doing this is to think about ratios of parameters. And one thing that was proposed was the idea of the first nonlinear coefficient, or a quality order parameter, typically called Q. And this is really a ratio of the third order harmonic to the first order harmonic. And the way you can think about that is if you remember how you expand sine x, when you expand sine x, you get an x term, and then you get an x cubed term. So the ratio of those two terms goes like x squared. So we certainly expect this ratio should go quadratically with the strain amplitude. And that's been shown very nicely by Manfred Wilhelm and colleagues. And so here's a series of measurements for a series of very nice commercial polypropylenes which have purely linear chain structures. So you can measure the magnitude of the Q parameter, and this can be related to, for example, the polydispersity of the material, or when you start to see strain stiffening or strain thinning in the material. One thing to bear in mind about these kinds of information, though, is that you're collapsing a lot of information into a single material quantity. So I've shown here that the ratio of I3 over I1 really contains 4 coefficients. It contains E3 and V3, as well as E1 and V1. So there are many different combinations of those variables that can give you the same ratio. So it's simpler to understand, but you are losing some of the material response that you've just worked so hard to gather. The nice thing about an information like I've plotted here, however, is that you can start to see what happens if the material is no longer, say, a simple linear chain. So to do that, you really want to connect it to a molecular theory. And the first one that was really done for this was done by Dale Pearson, where he used the reptation model. And he went through all the analysis, thought about larger and larger strain amplitudes, and he gave explicit predictions for these nonlinear coefficients. So as an example, I've shown you here the first third-order coefficients, where he basically thought about what happens when the chain deforms and the entanglement positions move. So we can actually compare, say, our mechanical measurements with that theory. And if I take the ratio of those harmonics, then it turns out that the third-order coefficient divided by the first-order coefficient comes out to just be 1/3 of the reptation time times the frequency, all squared. And so all I have to do is do a series of measurements at different frequencies, and you can actually relate the slope of that curve. It should be quadratic, as I've shown here, but you can actually relate that to a measurement of the relaxation time. And you can see as the molecular weight increases from 76,000 up to 300,000, that you can see the reptation time of the material increasing. If you now put chain branching in, so you now make a series of materials that have progressively longer and longer chain branches, then the shape of this curve changes, and you can again relate the shape of that curve to relaxation processes in the material, provided you have a molecular theory that can relate, say, these mechanical measurements to the measured response. And you can see here, for example, the green curve and the red curve. As the molecular weight of the arms get longer and longer, you can see that clearly 2 different relaxation processes appear. One is due to the chain backbone, and the other one is due to the arms moving. And what I'll show you on the next page is that we can actually relate that to a molecular theory. So Manfred Wagner and colleagues have actually developed a particular kind of theory called a molecular stress function theory. Just one example of a molecular theory for branch chains, but it gives you an explicit prediction for how this ratio I3 over I1 should appear. And it depends on 2 coefficients, alpha and beta, as I've shown you here, which are to do with how the chain orients and with how the chain stretches. So by taking your measurements of, say, these ratios or these nonlinear coefficients, you can actually probe the nonlinear properties of the material and relate it to the nonlinear coefficients in the constitutive equation. And again, I would emphasize that as the strain amplitude goes to 0 here, so as gamma 0 goes to 0, you see this ratio goes to 0, and that means that there is no nonlinear response at small strain. So you can't measure these parameters if you only have a linear experimental measurement. They use this intermediate region where only the quadratic terms are important. They call this moderate amplitude oscillatory shear, or you might call this mouse flow. Okay, so now I want to change gears a little bit and move to a more complicated kind of material. So these are kinds of materials that have a yield stress. And so the kind of question you frequently ask is, I know this material is viscoelastic, it looks like it's got a gel-like character, but if I deform it a lot, then it starts to flow. And so a question you might ask is, how yield stressy is my material? Or in other words, how big is the yield stress? Is that big compared to the modulus? Is that big compared to the viscosity? So there's a well-defined set of experiments you can already do for yield stress materials. You might do steady flow curves, you might do thixotropy, you might do small amplitude measurements. But all of those different measurements are really projections onto this Pipkin diagram. And I want to show you how you can use large amplitude oscillation as a way of probing things such as maybe a simple yield stress material like a carbopol gel, but also more complicated materials, maybe, for example, highly filled systems such as maybe a drilling mud or other kind of material that has particulate components as well as a yield stress. And so again, what we're going to do is we're going to connect the linear part of the world, which is small amplitude, to the nonlinear part of the world. To do that, you typically really want to use a rheometer in its controlled stress mode because you really want to probe stresses below this critical stress and above the critical stress. So for that, you really want to use a large amplitude oscillatory shear stress, or to distinguish that, I'll call that LAOS stress. But the idea is that we're putting in an oscillating stress now, and we're measuring the strain. Okay, so to do that, again, we're going to have an elastic component. That's the strain that's in phase with the stress. And then the component that's out of phase, which I've written in blue here, is what I would call a viscoelastic material property. And because we're now putting stress on one side of the equation and strain on the other side of the equation, the coefficients that relate these things are called compliances. They're typically given the symbol J. And you can see that there's an infinite series of elastic compliances, J primes, as well as viscous compliances, J double primed. We've developed a theory and a formulation that allows you to again describe those in terms of Chebyshev polynomials. And we call those coefficients compliances, C sub n in red here. Or for the viscous component, because it's got units of 1 over a viscosity, we refer to that as a fluidity, and it's typically given the symbol phi, as written here in blue. And so here's a typical response shown. Here's a Lissajous curve, where again it looks like, at small strains, it looks like an ellipse. That's at a stress below the critical stress. But you can see when the stress becomes larger, that no longer does this thing look like an ellipse. It now looks like something more like a rectangle. And what's going on inside there is really a sequence of different physical processes where there's a linear range where the material deforms elastically, and then it flows at a critical stress, and you get a large amount of strain until the stress gets small again, and then it becomes a solid again. So the characteristic hallmark of these things is these kind of rectangular Lissajous curves. Okay, so now that we're thinking about this, we really have to be careful because the shapes of our curves are very different. And I've shown you both an example of a typical model, say the Bingham model, as well as a generic sketch here. And the thing to remember is that what we're going to do is we're rotating the curve so that instead of stress being on the y-axis, we're really rotating this so that now stress, which is our control variable, is on the horizontal axis. And what we measure is the strain is on the vertical axis. And if, again, I come back to our demonstration example, this is a material that we can think of as having a yield stress. And at low stresses, it looks like a solid. If I put a large enough stress in it, then the material becomes something much more like a step function or a chair like this. And so the shape that you see depends on whether you're looking at it side-on or whether you're looking at it face-on. So does it look more like a rectangle, or does it look more like a chair from side-on? And again, remember, it's basically three-dimensional projections shown in a two-dimensional space. Okay, so we've developed the framework to do this. It's exactly the same framework. Essentially, you're just plotting the controlled variable now being stress. And so here's an experiment with a carbopol gel in a small strain or a small stress limit. Then the material is elliptical. And you can measure a small strain compliance and a large strain compliance, and they're the same. And the compliance has units of 1 over stress, so it's got units of inverse pascals. Once you get into the nonlinear range, however, then you see that the material actually becomes nonlinear, and the compliance at small strains, J primed M, is different than the compliance at large strains, which we call J primed L. And so the material is, again, here, you can see it's more compliant at large strains or large stresses, and so it's really a stress softening material. And that's typical of many plastic materials. They're hard until you put large stresses on them, and then they become more plastic or more viscous in their character. Final thing I'll point out to remind you is that, again, in the small strain limit, it doesn't really matter whether you have a controlled strain rheometer or a controlled stress rheometer. They both give you the same information. Okay? They must give you the same information. And most rheometer software has a way of converting between the elastic moduli, G primed and G double primed, and the compliances, J primed and J double primed. That's been well known how to do that. It's well described in John Ferry's book through calculating a relaxation spectrum or a retardation spectrum. Okay? However, that is not true when you're in the nonlinear range, and so whether you do a controlled stress experiment or a controlled strain experiment, you actually will get different measures of the material properties. You have to be very clear about which one you're doing, and I'm showing here both a strain-controlled experiment and a stress-controlled experiment plotted on the same axes, and you can see that although they look like they have the same shape, the material is still the same, the actual material measures that you get are different because in one case you spend longer at large strains, and in the other case you spend longer at large stresses. And so you have to be very careful when you're reporting this information. One measure that's, again, very useful in all of these things is the area enclosed by these curves. That's a direct measure of the energy dissipated in the material, and so I've given it the symbol E here, and it's really the cyclic integral of the area enclosed in these curves. It's the integral of stress times strain rate times time, and so it's the energy dissipated in the system. A purely elastic material would have no area enclosed. It would just be a line. It doesn't dissipate any energy. And you can see that a perfect plastic material, or a material that has a yield stress, it flows, it deforms, and you can see that the curve on the right here has a much larger area, so it's dissipating a lot more energy. Okay, and so we might want to compute those in a minute. And then again, I'll just show you one more rendering in 3 dimensions just to give you this idea of these curves looking like chairs, where here I'm plotting stress on one axis that we controlled. We measure the strain and the strain rate in the system. You can see the linear range. It's a very, very small linear range at small stresses, and this is again for carbopol. And what this chair looks like depends on whether you're going to look at it from one axis or another. So if I rotate this curve, then if I look at it as the measured strain rate as a function of stress, you can see the critical stress where the material suddenly starts to strain or flow a lot. If I rotate the curve by 90 degrees, you can see that it's a plastic material. It dissipates a large amount of energy, and you can see that it spends a large amount of time in the linear range where the line is straight. That is the compliance of the material. And then there's a region where the strain increases a lot. That's the flow regime in the material. And so again, you really have to remember that these things are 3-dimensional surfaces. One other thing to remember if you're doing a controlled stress experiment is that now the strain and the strain rate aren't any longer orthogonal. They're not the input variables, they're the output variables. And there's certainly no guarantee, except in the linear range, that they're orthogonal. So if you want a physical interpretation of these kinds of shapes, and you can only see them in 2 dimensions, the way I think about it is to think about the sequence of processes that go on. And so there's a region where the material deforms elastically at the top of this curve. Then there's a sudden yielding event at a critical stress, and then there's a rapid region of plastic flow. And if you think about this in a cartoon sense, you're running along, you suddenly run over the cliff, but in a normal flow experiment, the material then flows forever. In an oscillatory flow experiment, you then reverse direction, and so if you're a road runner, you can actually run back onto the cliff, and the material becomes a solid again. So again, you're capturing all of the information about the material in a single oscillating experiment, and you get some idea of the critical range of stresses. So let's take a look at our Bowditch curves, or our Lissajous curves here, and build up a Pipkin diagram for a viscoelastoplastic material. And so they're plotted here as a function of frequency on the horizontal axis, and now the stress amplitude on the vertical axis. And so you see the linear range. You can see that a carbopol gel is actually an elastic material. Then it becomes a viscoelastic solid. And then at a critical stress that looks like it's somewhere between 50 and 100 pascals, you start to see these curves becoming rectangles, and that's where the material is beginning to flow. So you can see that the critical stress that we normally think about as a yield stress is actually both a frequency-dependent and a stress-dependent kind of quantity. And so it's really not a single number. It depends on the frequency or on the time scale of the experiment. So let's focus on one particular vertical slice through this. So we'll pick a frequency of 5 radians per second, and let's compare the results. And so I've shown here the strain on the vertical axis, the stress on the horizontal axis, and you see that the linear range in these materials is very small. Okay, so at small stresses, the material is linear, but then as you go to larger stresses, suddenly the strain increases a lot. And the way that's captured is by thinking about the area of this curve, so the area captured by this curve. I can plot any measure of this curve. So here I've plotted the large strain compliance, or J primed L. And a simple theory like a Bingham model or an elastic Bingham model would predict a constant value for the compliance here. The way you can see this material is softening is by plotting the compliance, and you can see that the compliance actually gets larger and larger and larger until a critical stress, and then the material flows. Okay, so it's very easy to see that it becomes a nonlinear solid, and then the material begins to flow, all from this one coefficient that you can measure in LAOS. The other thing we can do is we can actually, again, use these kinds of measurements to compare with theories. And so we've recently developed a model for these kinds of materials that captures the elasticity and the viscoelasticity and the yielding character. And without going into the details of this 5-parameter model, it's shown here by the red curves overlaid on the blue measurements. And so you can see that we get a good description of both the initial elastic properties, then the viscoelastic properties, and then the yielding properties. And we can compare quantitatively the predictions of a model, or our model or any other model, by, say, calculating the area of this curve. And so that's the energy dissipation. And if we plot the energy dissipation, the blue points here are the experiments. The red line is our theory, and you can see that we capture the energy dissipation in this material and how it changes as you increase the stress amplitude. If you were using a simple elastic model, that's shown as the dashed curve here, and you can see that below the critical stress, there's no energy dissipation. It's a perfect elastic solid, and that's a poor approximation for many real materials. So again, we can use this kind of data to calculate constitutive properties. So in the final part of this talk, I now want to have a few words of caution. So all of this is done the way we would normally do a rheology experiment. That is, we put the material in, we deform it, and we don't really ask what's going on inside. But in many complicated materials, you also have to ask, what's the deformation inside my material? And so that's where techniques such as PIV, neutron scattering, X-ray scattering, ultrasound really allow you to look inside the material. And so I'm going to give you just a couple of examples of that where I'm going to look inside the material and I'm going to use that worm-like micellar fluid. And we know that the characteristics of a worm-like micelle, as shown in the plot here, is that the stress approaches a plateau. And so we're going to look inside. Okay, so here's a Pipkin diagram for a worm-like micellar fluid undergoing this process of shear banding. And what I've shown you here is the Pipkin diagram with frequency on the horizontal axis, and now the Weissenberg number, or the measure of flow strength, on the vertical axis. The small plot shows you the flow curve. It shows you the stress and the strain rate. And you can see that there's a large region where the curve looks like it's almost vertical. Okay? That's the example of a plateau. And so the stress in the material is constant, even though there are two very different shear rates. And if we do PIV measurements, you can see that the top half of the sample is deforming very fast, and the bottom half of the sample is deforming at a much lower shear rate. And people in the last few years have been very interested in constitutive models that can describe this transition between linear viscoelasticity, shear banding, and then eventually at high shear rates you can get to a region where there's no shear banding again. So we've done PIV measurements. Lettinger and Rogers have done some very nice measurements in neutron scattering, where they've actually used neutrons to look inside and look at the internal structure of these kinds of materials. So definitely be careful about what's going on inside. And to do that, I'm going to just take you through a few steps of how you might do that. So we've built a PIV system where you actually shine a laser in through a glass top plate. You use a video camera to look at the deformation field. And what I'm showing you here is a movie of what you see at small strain amplitudes. And so you can see that the velocity profile looks like it's going backwards and forwards in the images here. If we actually quantify that using our PIV system, then here is the velocity field. And so you can see that there's no slip at the bottom plate or the top plate, and the velocity field is indeed oscillating as you'd expect. Okay? That's in the linear viscoelastic region. As the material starts to become nonlinear and shear band, however, then things become more complicated. So here's the velocity field in a large amplitude oscillation, and you can see that the fluid is moving, certainly from left to right, but you can see that in the middle of the material there's a shear band, and you can see that the position of that shear band actually is time dependent as we go forward. And so if I measure the velocity field here is the velocity field, and you can see that the position of the band and the extent of the band depends on both the time and the strain amplitude that we have. So it's linear, and it becomes progressively nonlinear at large shear rates, and then when the flow reverses, it comes back and is linear, and then becomes nonlinear again. So if you can't see inside a complicated material, then that could indeed be affecting the nonlinear rheology that you're measuring. To quantify that, we can combine these velocity field measurements with our stress measurements. So we do both measurements at the same time. And in this nonlinear regime, what you start to see is the Lissajous curve becomes clearly non-sinusoidal or non-elliptical. And you start to see the appearance of higher harmonics. And so the velocity profile is now no longer linear. So you have to be very careful with things like micellar fluids and materials that shear band, because that can disrupt what you're trying to measure inside. I want to emphasize, however, again here that it's not slip in these measurements that's important. And the way we've done that is by carefully measuring in the middle plot. The blue curve is the velocity profile that's measured by the rheometer, and then the red dots are the measurements that we make from our video images. And you can see that by treating the surface in a particular way to make it philic or wetting by the micelles, then we get perfect non-slip. This is a real rheological nonlinear deformation of the material. And as a final example, this is an example from Norman Wagner and colleagues at Delaware. This is an example, again, of a large amplitude measurement where you can see a three-dimensional rendering of both the stress as a function of the strain and the strain rate in the middle. And then you can also see measurements of G primed and G double primed and how they decrease as you go to large strain amplitudes as you fall off the plateau. But this is done in a neutron beam, and so at the same time, they can also measure the structure function of the material. And so what you're seeing in the top right is indeed variations in the structure function as you go to larger and larger strains. And the fact that it starts as a circle and then becomes progressively deformed is again related to the deformation of the microstructure inside the material. And if you're interested in learning more about that, I've given you a reference to some recent work from the Delaware group. Okay, so I think in conclusion, what I've tried to do in this lecture is introduce to you this new idea of a framework that we call LAOS, or LAOS, as a way of characterizing nonlinear rheology. Key thing to bear in mind is it builds on linear viscoelasticity. So it starts with something you know, and it builds into a framework that is more complete. You can either do that with oscillating strain, so what I call large amplitude oscillatory strain, or you can do it by oscillating the stress, or LAOS stress. Just bear in mind that in one you measure modulus, and in the other one you measure compliance. And what you're really doing is running into the nonlinear regime. You're running over the edge of that cliff and deforming the material in a way that's probably very important if you're interested in, for example, processing of your material. So linear viscoelasticity is great for small strains. When you fill a bottle or you fill a mold, you're typically in the nonlinear region of the curve. I've tried to introduce to you a visual language, a way of doing this by thinking about Lissajous curves. They're very visual. They're very easy to explain to colleagues and co-workers when the material is linear and when it's nonlinear. But if you really then want to, say, differentiate between maybe one formulation and a competitor's formulation, or between one grade of polymer and another grade of polymer, you really need to distill it down into some quantitative information. And that's where these Chebyshev coefficients, or these nonlinear moduli, are a useful way of saying this material is linear to a certain strain, this other material is more nonlinear or less nonlinear. So it's ultimately, I think, a way of building up a database, just like we can all be differentiated by our fingerprints. Every grade of material should be differentiated by its own rheological fingerprint. And then finally, current work in the field is really related now to connecting these macroscopic properties down to the microstructural deformation. And with that, I'd just like to acknowledge the people who did a lot of the work. A lot of what I've shown you here comes from Randy Ewald's doctoral thesis at MIT, as well as additional contributions from Thomas Ober and Chris Demetriou and Trevor Ung, and then the sponsors that are shown here. With that, I'll be very happy to answer questions, and I'll hand it back to Adil.
Thank you, Gareth. A recorded version of this webinar will be archived and available online through the TA Instruments website.